Okay, then welcome back to the last session of the day, and Joris Ceulemans will tell us more about substitution,
Yes.
which is a hot topic here.
Indeed, indeed. So yeah, I guess everyone by now knows what substitution is and why it's important. But probably fewer people have heard about multimode type theory. So I'll start my talk by introducing this system. And I'm going to do that by an example, and the example is guarded recursion. So there it is again. However, it will be a kind of a different flavor than what we saw in the last presentation. But still. So here we have, we're trying to define an infinite stream of natural numbers in AGDA. And so it's just a stream 0, 1, 2, 3, etc., etc. And so how is it defined? Well, we say, okay, the first element is 0, and then the rest of the stream is obtained by mapping the successor function to the stream nuts that we are actually defining. So it's a co-recursive definition. And as you can see, there is some colored background here, which is not a good sign. So AGDA is complaining about something. And which part of AGDA is complaining? It's the productivity checker. So the productivity checker, it works for co-recursive definitions, and it's kind of the analog of the termination checker for recursive definitions. So it will make sure that our definition of the stream is productive. So every element of the stream can be obtained in a finite number of computation steps. And so the productivity checker is not happy. I'm not going to tell you how it exactly decides that it's not happy, but actually it's wrong. So just like the termination checker is imperfect, it sometimes makes the wrong decision. Well, in this case, the productivity checker also makes the wrong decision because this definition actually is productive. How can we see that? Well, we start with a stream that starts with a 0. And if we then map the successor function over all the known elements, we see that the second element is 1, and we can repeat that, and you see, well, every element, we can compute it in a finite number of steps. So actually, this definition is productive. So how can we solve this problem? Well, for that, it's also crucial to note that the fact that this definition is productive crucially depends on the fact that we have here all these straight arrows. We could, for instance, also replace this map_suc function with some function that swaps two elements, and then our definition wouldn't be productive anymore. And still, it would have type stream n to stream n. And so the idea of guarded recursion is a little bit that we're going to keep track of this recursive behavior of functions, or this co-recursive behavior in their type by use of these modalities. So that's where the modal type theory comes in. Now, before I want to continue this example, I want to say a little bit about multimode type theory or multimodal type theory. Those are the same things in general. So it's a system introduced by Gratzer and co-workers in 2020. And actually, it's not just one type theory. It's a framework for modal type theories. And it's parameterized by what they call a mode theory, but I'm going to talk about a mode system here because I think that's maybe a better word for it. And such a mode system is basically just a small 2 category. Now, don't worry for the people who were here yesterday. I'm not going to dive deep into the world of 2 categories. We just need to know what they consist of. And so the objects, or the 0 cells of our 2 category, are called the modes of our mode system. So we have a couple of modes, and at every mode in MTT, we're going to have an entire instance of Martin-Leuven type theory, so complete with function types, sigma types, natural numbers, etc., etc. And so every term, every type, and every context in MTT lives at a certain mode. Now, if we only have these modes, then we would have like just separate copies of Martin-Leuven type theory. That would not be very useful. But fortunately, there's also the morphisms, or the 1 cells of our mode system, and in the mode system, we call them the modalities. So if we have a modality mu from m to n, then we get some new primitive operation on contexts, or, well, a new constructor from context, let's say. So we get a lock mu constructor that takes a context gamma at mode n and produces a context gamma lock mu at mode m. And similarly, we get a new type constructor that takes a type t at mode m in context gamma log mu and produces a modal type mu t at mode n in context gamma. And so you can think of them as a little bit as this one being left adjoint to that one, but I'm not going to make that precise in any way in this talk. Okay, and then of course we have a 2 category, so there should also be 2 cells somewhere. So if we have a 2-cell alpha from a modality mu to modality rho, then intuitively we get a coercion function from the modal type mu t to rho t at mode n. That's the intuition. We can actually implement that, but the 2 cells will also be important in some other cases that I will come to in a couple of slides. Right. So let's head back to guarded recursion. So now we can instantiate this framework MTT with a mode theory to obtain a guarded recursive type theory. And this will be the mode theory. So we have 2 modes, a mode omega and a mode star. And we can think of, to make the connection with the previous presentation, you can think of this as being a world where there is 1 clock and this as being a world where there is no clock at all, right? So here, values can, intuitively, you can think of them as if they unfold over time and they make some more information at every time step. Here, at mode star, you can think of values as if they're just static values. There's no time dependency there. And we can also explain these modalities here using that intuition. So this modality kappa, it takes a static value and then makes an unfolding value out of it that actually does not unfold. Everything is there from the beginning. This phi modality takes an unfolding value and just unfolds everything at once to get a static value. That's basically the clock quantification from the previous presentation. And then, of course, there's the later modality, which takes an unfolding value and just shifts everything by 1 time step. Everything gets delayed by 1 time step. Okay, so I've written some equations here with these modalities. They will not be important. What will be important is that there is a 2-cell, which I call advance, from the unit modality at mode omega to the later modality. So intuitively, we get an operation of this type that allows us to send something into the future. So that's for the mode system. Now we also need some type and term constructors for working with streams, with guarded streams. So for every type A at mode star, we get a new type of guarded streams of A at mode omega. And you can see them as unfolding over time because they make available 1 more element of their stream at every time. So in the beginning, we just have 1 element, the first element of the stream, and at every time step, we get 1 more element of the stream. And so that explains why the tail of such a guarded stream has not type guarded stream, but type later guarded stream, because the first element of the tail is the second element of the original stream, so it's not available now, but it's only available 1 time step from now. And also there is this kappa here, because A was a type at mode star, and we want to embed it into mode omega by using this modality kappa. Right. The last thing we need is loop recursion. So as you can see here, every variable in MTT appears in the context under a certain modality. So here we have a context gamma that is extended with a variable x of type t, and that is bound under a later modality. Now, if in such a context we can produce a term of type t in mode omega, then by loop recursion we can construct a value of type t in the original context gamma. So this is actually, it models co-recursive definitions. So this variable x will actually be your co-recursive call. So this loop recursion actually is some kind of a fixed point operator. And I've not told you yet how you can use variables in MTT to produce terms, but what I want to say here is that this later modality here will make sure that everything that you write using loop recursion will actually be productive. Okay, so how do we write a program in MTT then? Let's try to implement the stream that we did in AGDA and about which AGDA complained, so the stream of natural numbers. So we are in an empty context. We want to produce a stream of natural numbers. As we saw, that was a co-recursive definition. So the first thing we do is we are going to apply loop recursion. That gives us a variable s in our context, which will represent the co-recursive call. And now we're going to construct a stream. So we're going to use this const constructor for a stream. And as I've shown on the previous slide, that's a modal function. So it has these arguments with these modalities. Which means that when we apply this function, then the arguments will get type checked in a context where we apply this lock operation to the context. So this means that, for instance, here in hole 0, well, we have this modality kappa here, so our context gets logged by a kappa. And the same is true for hole 1, but then with a log later. You can also think of this log later as like the tick that Micah talked about in the previous presentation. So evidence that some time step has passed. Okay, so now the head of this stream should definitely be 0. 0 is a valid term in any context, so that's easy. And then for the tail, we want to use some map operations. So we have a map operation for guarded streams. I will not show the implementation. Note again that we have this kappa here, so that means that when we want to give the function, we have again a log kappa here, but still the successor function is also valid in any context, so that doesn't matter. And now here we want to have our co-recursive call, so that means that we actually want to have our variable s here. Now with MTT, if you want to apply, if you want to use a variable s in a term, there is one condition you must check, namely, you look at the modality under which that variable appears in the context, and that should match the composition of all the logs to the right of that variable. Now there is only one log here, which is also later, so in this case, we can use this variable s here, and this is a valid MTT term. Okay, now actually I've lied a little bit about this condition. The condition in MTT is a little bit less strict, so I'm going to give another example. So here we're defining the stream toggle, which is just 0, 1, 0, 1, 0, 1, etc., etc. The definition is very similar, so we use lerp recursion, and then we apply this const constructor twice. And because we have applied it twice, that means that we have 2 times this log later here in the context. And now we actually want to use this variable s here, but of course this later does not match the composition of these 2 later modalities, which is later squared. Later and later squared, they're not the same. How can we solve this? Well, fortunately, the condition is not that strict. The only thing that we need is actually there should be a 2-cell from this modality to the composition of this modality, these 2 modalities. So there should be a 2-cell from later to later squared. Can we find such a 2-cell? Well, yes, we had this advanced 2-cell from the unit modality to the later modality, and so by whiskering, we can, or by horizontal composition in our 2 category, we can find a 2-cell from later to later squared. It's not really important what this 2-cell is. The important thing is that it's there, and so we can use it to produce, to use this variable s here in our term. Okay, so I've talked a lot about MTT for now. Let's throw some substitution in. So how are we going to do that? Well, I have here again this definition of guarded stream of toggle, and we now want to express that this is actually propositionally equal to 0 cons once cons toggle again. That should be the case that these 2 are propositionally equal. Or more general, we want to express that terms produced via lerp recursion are actually fixed points. So actually, we can express it as follows. So a term produced via lerp recursion should be propositionally equal to the term t, where we replace our co-recursive call, or this variable x, with, again, the same lerp recursive term. And so our instance of MTT for guarded recursion will actually contain another inference rule that witnesses this propositional equality, or more or less, because actually this propositional equality is not well typed. And how can we see that? Well, for that we need to look at the MTT rule for context extension. So when is a context of type of the form gamma extended with x, when is that well formed? Well, we need to have a modality mu from a mode m to n. Of course, gamma should be a valid context. And then we should have a type s in the context gamma locked with mu. And that mu here is essential, because that means that if we want to produce a substitution from gamma to gamma extended with x, by substituting x with some term s, then this term s should live in a locked context. That's the only way we can make sense of this. That's the only way everything lives at the right mode. But if we apply that to our situation, so we have our term lerp here, which lives in an arbitrary context gamma, but then t lives in a gamma extended with some variable under the later modality, which means that if we want to substitute this variable with some term, then that term has to live in context gamma log later. Wait, here, gamma log later. But this loop term lives in context gamma, not gamma log later. So how can we solve this? Well, fortunately in MTT, we have a thing called key substitutions. So for every 2 cell, we get a bunch of substitutions called key substitutions. And in the case of our advanced 2 cell, for every context gamma, we get a substitution from gamma log later to gamma, which we can apply to our term here to obtain a term in gamma log later. Okay, that already seems quite complicated, I guess. Let's go further. So, yes, of course. So what can we do? So if we apply this here to our construction of this toggle stream. So here we have this substitution that we get by applying substituting S with this term here, and we apply it to everything to the right of loop. So we get to this, and now MTT has a bunch of definitional equalities that tell us how you can push this substitution through the constructors. But one of the problems is that, recall that here, with the 0, we had locked our context because this const constructor is a modal function. There was a modality there. So we have locked our context, which means we cannot just apply sigma to this because sigma goes, it has the wrong domain and codomain. But fortunately, MTT has another constructor for substitutions, so we can also lock those, and that means that we also apply the lock to domain and codomain contexts. And we can use that to push this substitution through, and the same happens with the second argument, but then with a later a lock later. Now, of course, 0, it doesn't contain any variables, so applying a substitution should actually do nothing, and indeed it does so, and MTT also has a definitional equality witnessing that. And for the second argument, we can push this, do the same thing, push it through, and of course, for 1, we get the same thing, and we end up with this term where we have here a variable and we apply some large substitution through it. And now we're completely stuck, like what should we do with this? That's not clear at all. So I hope at this point that I've convinced you that substitution in multimode type theory is a very difficult thing. So the substitution calculus of MTT is very complex, and a substitution in MTT is not at all a mapping from variables to terms or a list of terms in case of the Brown indices. We have keys, we have these locks, etc., etc. And so furthermore, MTT has explicit substitution, so it has an explicit constructor for applying a substitution to a term, and then it has a bunch of axioms, you could say, a bunch of definitional equalities that say how these explicitly substituted terms interact with other term formers. So a priori, it's not at all clear that we can compute all these substitutions away, that every term in MTT that has some explicit substitutions is definitionally equal to a term without any substitutions. So the question is this the case? And moreover, we want actually to compute these substitutions in a structurally recursive way. We want to actually implement this in a proof assistant because all of this work actually stems from the fact that we want to implement this in an Agda library called Sickle that we're developing. And so yes, can this be done? Well, the answer is yes. So the answer is described in a paper that we submitted to the Types 23 post proceedings. So how do we do this? So we have here 2 systems. The first one is well-scoped MTT, and the second one is substitution-free MTT. So both the similarity between both systems is that both are extrinsically typed, but intrinsically scoped. So every expression, every term, every type appears relative to some scoping context, which contains, which is basically just an MTT context, but with all the typing information erased. And actually, we also erase the names because we use the Brown indices in these systems. And then well-scoped MTT is basically just really MTT with but extrinsically typed. So all the other details are, we try to more or less make them the same as in the presentation of MTT. So we also have explicit substitutions, and we also have the same substitution calculus and an entire system of axioms that give us these equalities between substitutions and substituted terms. On the other hand, SFMTT has no constructor for applying a substitution to a term. But there we actually want, so there's also a notion of substitution, but it's different from this one. And we also have an algorithm or a function that we implement, and we can apply it, and that algorithm allows us to apply an SFMTT substitution to an SFMTT term to obtain another substitution-free term. And so how do we implement this? Well, that goes in 3 stages. First, we say what happens when we apply an atomic renaming. So in atomic renaming, we already include locks, keys, and then we can, of course, rename a variable with another variable. And then in the second stage, we say what happens when we apply an atomic substitution. It's basically the same, but we can we can substitute a variable with a term and not only a variable. And crucially, there is no composition. So these atomic substitutions, they're not closed under composition. And then as a final step, we say what happens with general substitutions, which are closed under composition. So why do we need these 3 stages? Well, part of the answer was already given in the talk by Dima this morning. In order to say what happens here, we need to be able to lift substitutions, and for that we need renamings. But in MTT there's also another reason. So here we have again that huge term that we had some slides ago, but we're going to make it less huge now. So basically what we want to do is we have a substitution, we substitute S with some term, and here we have our variable S. So intuitively, this should just be this term, right? But actually, the problem is that this variable, it lives in a context with twice the lock later applied, and this term lives in a context with just once the lock later applied. And so the only thing we need to do here is just apply another key substitution to this term. That's also what MTT says that has to happen. However, if we want to do this in an algorithmic way, and this were a substitution, then our entire algorithm wouldn't be structurally recursive anymore. And so fortunately, we can make this, this operation here in our algorithm an atomic renaming, and so that resolves the entire circularity problem. And so of course, then finally this toggle here, I've written the definition here, so it's actually a closed term. So applying these 2 substitutions actually does nothing, and we end up in where we actually want to be. Right, so my final slide. So here we have our 2 systems. Here we have our algorithm, here we have the axiomatic system. The fact that we have this algorithm here lets us implement a translation function, so we can translate every term in well-scoped MTT to SFMTT by just actually computing away all the substitutions. And we can also trivially embed SFMTT to well-scoped MTT. And then we've also proven a soundness and a completeness result about our substitution algorithm. So soundness says that if we start with a term here, we compute all the substitutions away and then embed it again, then the axiom system of WSMTT will say that this is equivalent to the term we started from. And the completeness says that if we have 2 terms here that are told to be equivalent according to the axiom system, then computing away the substitutions actually gives us the same result. And this is completely proven in our preprint, which you can find here. And that's everything I have to say. Thank you.
So we have time for one short question.
This reminds me a lot of something that was presented at Types last year. Ambrouche Kaposi has a similar story for CWF, where you also, like the usual way of presenting CWF, you also have explicit substitution and an explicit substitution calculus, but then you have a bunch of transport all over the place, which make everything very messy. And so you can kind of re-implement the version with a strict substitution that computes definitionally in a very similar way. So I don't know if you were aware of this, if you know of
No,
if there's deeper connection of just this looks the same, or
I have to look into that.
Okay,
yeah.
I can give you the reference. Yeah.
Mm-hmm. Yeah. I see. Yeah.
So I think, well, in light of time, we will have to postpone discussions.
Okay.
So thank you very much.